Hello, this is Mr. Craig, and I think this is day 4. Not 100% sure, but today we're going to talk about chemical bonding, writing chemical formulas, and discuss the mechanisms needed to write a correct chemical formula or naming the chemical formula. First thing that we need to talk about are chemical bonds, and we will go into greater detail as the year goes on, discussing some of these intramolecular forces, but for today you don't need to be so concerned about the intramolecular forces, the forces between atoms. But it's nice to review it real quickly here. So chemical bonds, the forces that hold atoms together in a compound, and these are covalent bonds for the most part when we're looking at a nonmetal with a nonmetal. Anytime you hear the word covalent, the first thing I want you to think of is sharing, because in covalent bonds they're sharing electrons. Molecular bonds are a collection of covalently bonded atoms, so we'll talk about these a little bit later on. Chemist shorthand formulas. First thing we want to do for writing the chemical formulas, first of all, indicate the correct symbol by writing, or indicate the correct atom by writing the correct symbols. So if you're using carbon, hopefully you'll write the letter C. And then the subscript is used immediately after the atom to indicate how many of an atom you have. Now, if there's just a single atom represented in this formula, there's no need for a subscript. So if you're writing carbon monoxide, which has one carbon and one oxygen, there's no need to put C with the subscript 1, O with the subscript 1, since we already have our ones indicated there. So here's an example, carbon dioxide. You have one carbon and two oxygens. The structural formula are individual bonds shown by lines, and when we draw Lewis structures or do things more with that, then we'll get into that a little bit more. But again, don't need to know that for today, unfortunately. Ions. Ions are charged particles, so it's either a positively charged particle or a negatively charged particle. Cations are a positively charged ion. When we look at, say, magnesium, that has a +2 charge. Ammonium, which is a polyatomic, has a +1 charge. And then the anions are negatively charged ions. And some examples of those are chlorine with a -1, or chloride, I should say, with a -1 charge, or sulfate with a -2 charge. Ionic bonding, again, is the force of attraction or the electrostatic attraction between oppositely charged ions. Periodic table, the elements are classified by their properties, their atomic number, the groups or the family, and we'll talk about this again when we discuss periodic tables. Group 1A, the column on the far left, is known as alkali metals. In other words, when we talk about your cell phone battery or any battery, very efficient batteries have lithium in them. Where do you find this alkali battery? In group 1A. Group 2A is alkali earth metals. Skip all the way over to 7A, and we have the halogens, and then the very last column on the right is your noble gases. The periods are the horizontal rows, and those really, until we do electron configurations, those don't have too much significance other than the energy level that they're in. So we'll talk about that a little bit later on as well. Naming compounds, you will need to know this for today's homework. Ionic compounds, binary just means that we have two different kinds of atoms. So the cation, or the more metallic, or the metal, is always written first. And then the monatomic cation just means that we have one of those. For example, calcium is a metal. How do we know that? Because it appears on the left side of the periodic table. There's a very, very small amount of elements that actually are nonmetals. And actually, let's see if I can get to that. Go to a periodic table here. I do have a periodic table up and running. Good. The small amount, and let me do this real quick. I'll get rid of that line there. I'll talk about that here in a second. The small amount of nonmetals are actually, if you put a dot in the middle of your carbon, and then a dot in the middle of the fluorine, and then a dot in the middle of the iodine, and if you're able to draw straight lines, and I'm not doing a very good job of that, if I had a much better writing utensil. These are actually any element that these lines are touching or within are considered non-metals. So when we talk about non-metals, this is a very small percentage of non-metals, and I call it the non-metal triangle, which you may hear me refer to later on. So when we discuss where the non-metals at, well, again, put a line in the middle of carbon, fluorine, and iodine, and then connect the dots, making straight lines. And so really all we care about are carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, and chlorine, selenium, bromine, and iodine. Yes, I know that I got part of my line in the arsenic and the selenium, but don't worry about it. The elements that lie along here, these are your metalloids. They can either be metal or non-metal, depending on the situation and who they're with. So we won't worry about those, but the non-metals definitely are over here. And then so that means, well, what are the rest of these elements? Well, everything else over to the left of that, the metalloids, are considered to be metals. Okay, so hopefully that clears that up for you. Let's continue on here. Let's see. Where am I at? Nope, we already did that. Let me get through that real quick. Sorry, guys. Okay, so got through the periodic table. All right, so naming the compounds. The really nice thing about the compounds is that when we look at the anion, we're going to take the root, like if it's, well, we've got chlorine here that ends in INE, then I'm going to drop the ending, the last ending, and put IDE. So chlorine, when it's an ion, turns into chloride. So if I wanted to make a compound made up of calcium and chlorine, I want to make sure that the algebraic sums equal 0. Until you're told otherwise, make sure everybody adds up to a neutral charge. So if I want to put these things together, calcium having a +2 charge, I only need one of those, and chlorine having a -1 charge, I would need 2 of those. So that I have a +2 and a total charge of -2, which equals 0. So naming this, I'd have calcium chloride. And notice that we don't do anything to the metals name. There's no Greek prefixes, which we'll talk about here very shortly, but we name it as is. The non-metal will drop the last syllable and add IDE to it. All right. Metal that is capable of forming more than one cation needs to have a Roman numeral in the name. So, for example, you won't be required to memorize these. You'll be required to recognize. And in this case here, you would never be given a formula unless I say, oh, okay, these have more than one charge. You need to tell me what they are. However, if I give you the name of the compound, there should be no question as to what you need to do. However, I'm telling you right now that lead has more than one charge. What are those charges? Well, we know one of the charges based on the charge of the nonmetal. From the last example, we know that chlorine has a -1 charge. How many chlorines do we have? We have 2. So that means that all of the nonmetals possess a -2 charge. And we know that this whole compound has to equal 0. Its full charge has to equal 0. Therefore, since I have one lead, what must the charge on the lead be? That's right, it has to be a +2 charge. So we're looking at a lead +2 ion here. And again, it is a cation because it's positively charged. So if I wanted to write this out, I would call this lead with a Roman numeral 2, because again, since lead has more than one charge, and I would tell you if it had more than one charge if I were giving you the formula. So since it has more than one charge, you have to tell everybody that this lead that we're using here for the PbCl2 has more than one charge. Which charge are we going to use? We're going to use the +2 charge and then the chloride. Okay. 10 polyatomics, make sure you know these. I think on the first day I said to have these memorized. You need to know these. That's why in Honors Chem we had you memorize these. And I know that some of your chemistry teachers gave you the 10 polyatomic ions with the charges, and there's a nice little sheet there. You need to take that sheet, tear it up, and throw it away. You need to know these. If you wish to do well in AP Chemistry, you have got to know these 10 polyatomics. Plain and simple. If you don't have these memorized by the time you arrive to school in August, you're going to be in some deep doo-doo. Seriously, if you don't have it memorized, especially since you were required to memorize it in Honors Chem, if you do not have these 10 memorized, you are in bad shape. So get these things memorized and know how to use them. Not only know the formula, know the charge, know the name. Okay? Know those. I'm trying to help you out here. If you want your life to be very, very easy in chemistry, you've got to know these 10 polyatomics. No ifs, ands, or buts. Do it. All right. Names of the polyatomics when you add or remove an oxygen. This one isn't as critical to know. Knowing the 10 is very important. However, this would be a benefit to know that if I remove one oxygen, okay, from the polyatomic, and there's only a few polyatomics that will do this too. So when we look at, say, the ammonium, well, number one, it doesn't even have an oxygen, so we don't have to worry about this naming system with this. Acetate, we won't take oxygens away. Those of you who are taking organic chemistry will find out the answer as to why you can't take oxygens away from the acetate without changing the whole structure and the whole composition of it. Hydroxide, we're not going to remove any oxygen away from that either. So really what we're doing is the next thing that I'm talking about only applies to 7 of the 10 polyatomics. Okay, so knowing that it only applies to 7 of the 10 should help you out and make you relaxed a little more. All right, so if we remove one oxygen from the polyatomic, it had an ATE ending, okay, like nitrate, iodate, carbonate, sulfate, so on and so forth. We're going to get rid of the ATE ending and make it ITE, okay? If I remove 2 oxygens from that polyatomic, we're still going to remove the ATE ending, but we're also going to include as a prefix at the beginning hypo, okay? So hypo, whatever it is, ite. So if I'm looking at, say, sulfate, it's SO4 with a -2 charge. If I remove 2 oxygens, the charge remains the same. However, now I have SO2 with a -2 charge. I don't call this sulfate. I'm actually going to call it hyposulfite, and it still has that -2 charge. All right, now if we go the other direction, say we start adding oxygens, the only thing that we're going to do is add the prefix per. So if I have my sulfate, SO4 with a -2 charge, and I add an additional oxygen to this, that makes it persulfate. Still ends with ATE. Okay. Now, you don't need to worry about why the charges don't change yet. We'll talk about that later on. Okay, just have faith. These charges for the polyatomic don't change when we add or remove an oxygen. Now, something is changing within that compound, but we don't care what it is yet. Be patient. All right, and as I said earlier, really big point here, even though we're adding or removing oxygens, the polyatomic charge does not change. Okay, the charge does not change on this. All right, some organic compounds. Be nice if you knew these. Not as important as the 10 polys. We will talk about this again once we get very, very close to the AP exam. I am not going to specifically require you to have these memorized for the first test, okay? But it would be nice if you knew what these were, okay? Notice that they all end in ANE. All of these end in ANE. And it has a generic equation where we have however many carbons we have, we're going to have twice as many plus 2 hydrogen, okay? We haven't talked about carbon and the type of bonding it likes to have. In organic chemistry, that's all you're going to talk about is carbon and the type of bonding it likes to have. Well, here you go. I'm going to give you a real quick Cliff Notes version of bonding with carbon. Carbon wants 4 bonds. Period. It doesn't want 3. It does not want 2. It wants 4. Carbon will always have 4 bonds. And if you write out a chemical formula where carbon only has 3 or less bonds, it's wrong. Okay? So carbon wants 4 bonds. Plain and simple. All right? So, and that means that carbon won't have any lone pairs. That's probably a better thing. So when we look at our things here, the thing that you need to know is meth. That means I have 1 carbon. Eth means I have 2 carbons. Pro means I have 3 carbons. Bute means I have 4. Then after we get past 4, once we get past 4, then it jumps into our Greek prefix naming system. 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nano. 10 deca. Okay? So that's the ane ending. A-N-E means that we have 2 times the number of carbons plus 2. Okay? If it ends in ene, E-N-E, and again, you'll get this in regular or in organic, then however many carbons we have twice as many hydrogen. Okay? So it looks very, very similar to the ones that we just talked about with the A-N-E ending. Methane does not exist. Again, what did I just say not too long ago? Well, carbon wants to have 4 bonds. And if we only have 1 carbon, that means that we only have 2 hydrogens. So methane does not exist. You can say that it would be methane if it existed, but there is no methane. So don't ever try. You can say, okay, that there's a compound that is called methane that does not exist. It's a fictional type thing. Okay, now we could have methane. No, I'm not even going to get into it. Okay, so if you want to get ahead of the game here, and again, this is not for the first day, but again for the AP exam, knowing the ending E-N-E, and here's our generic formula. However many carbons, we have twice as many hydrogen. Okay? All right. Molecular compounds. Again, these are comprised of only nonmetals. Okay? Only nonmetals. The first element in the formula is named first. Brilliant. The second element is named as if we were naming it as an anion in the, say, the ionic compound. So we're going to take the last syllable or last 2 syllables, and we're going to add IDE. Okay? Also, we need to use the Greek prefixes, and I don't remember if I have them here. Let's see if I have them. I don't think I have them here. But here they are, and you might want to listen carefully. 1, mono. 2, di, D-I. 3, tri, like a tripod. 4, tetra. If you've ever played the game Tetris, there's 4 blocks. 5, penta, like the pentagon. 6, hexa. 7, hepta, H-E-P-T-A. 8, octa. 9, nano. 10, deca. Okay? So if you need to hear those again, just back up the video and you can listen to those again. Now, we must use Greek prefixes when we have a molecular compound or nonmetals with nonmetals. So use the Greek prefixes. However, we never use mono on the first element. We'll use mono on the second one, like carbon monoxide, but we wouldn't call it monocarbon monoxide. Okay, that's just the naming convention. It's okay. Don't worry about it. All right, so looking at this compound here where we have P2O5. All right, so we're going to name the first compound as phosphorus, and then the last compound, or I'm sorry, the first element as phosphorus, the second element as oxygen. So we have phosphorus and oxygen. However, since we have oxygen, that means we need to drop the E-gen. And we're going to call that oxide. So we're going to drop the E-gen and add ide. So we have oxide. So we have phosphorus, oxide. However, since we have a 2 here, that means that we have 2 phosphorus. So we have diphosphorus. And since there's a 5 here for the oxygen, we have pentaoxide. So diphosphorus pentaoxide should be the name of this compound. Now, if you want to hyphenate, like put a hyphen between the di and the phosphorus, that's fine. I don't have a problem with that. And if you want to call this penta with an A and then hyphenate it oxide, not a problem. It's fine. You guys are in the state right now, or in the mode of learning, and there's absolutely nothing wrong with writing it like that. All right. Naming acids. Okay. If you need to take a break, you can always pause the video. Naming acids. If an anion, nonmetal, does not contain oxygen, so there's no oxygen anywhere in this compound because, again, oxygen is a nonmetal. So if the anion does not have a polyatomic, that's probably a better way to say it. Since the compound does not have a polyatomic, then we want to use the word hydro at the beginning. Okay? And then what we're going to do is we're going to drop the last syllable or last 2 syllables, depending on the name itself, and we're going to add ic. So you're going to add hydro at the front, and then you're going to put ic. Now, this is a little bit different than the hypo that we had when we removed oxygens. Okay, there is no oxygen here. So there's never going to be such a thing as a hydro-hypo. Okay, won't happen. So hydro, no oxygen, and then drop the last syllable and add ic. Okay, so for example, when gaseous HCl, or hydrogen chloride, is dissolved in water, we call this, since there's no oxygen, we're going to call that hydro, and we don't do anything with the hydrogen because all acids start with hydrogen, at least one hydrogen. Sometimes there'll be more than one hydrogen, but they have at least one hydrogen at the beginning of the compound. That's how we know it's an acid. Hydrogen at the beginning. How do we know if it's a base? Hydrogen at the end. We'll talk about that later. Okay, so we have chlorine. There's no oxygen, so we're going to say that that's chlorine. Drop the ine and add ic, so we have chloric, but since there's no oxygen, hydrochloric, and then of course don't forget to put acid. So hydrochloric acid is the name of this compound. Okay, here's some examples. HF, so no oxygen, so that means we have hydro. Fluorine is our nonmetal here, so we need to get rid of the ene and make it ic, so we have fluoric, so this is hydrofluoric acid. Okay. Pause the video and try the next one here. Okay. And actually, I hope you haven't paused the video yet, but realize that all these acids are ionic compounds, so we never ever use Greek prefixes. Okay, so go ahead and pause the video now and try it. Okay, now you've had a chance. Again, this 2 here, why is that 2 there? This 2 is here because we need to balance charges. Remember, all ionic compounds have to have an algebraic sum of equal to 0. So we know that hydrogen has a +1 charge. What's the charge on the sulfur? -2. So that means we need to have 2 hydrogens here. However, since there's no oxygen, okay, we still start off with hydro, and then the sulfur, drop the last syllable in some cases, and this one you got to listen to it a little bit. It's actually sulfuric, so we didn't drop anything in this one. And if you called it sulfic, you know what? I'm not going to lose any sleep over it. I'm not going to get angry because you're following the rules of naming this. However, we don't worry about this 2 here because in ionic compounds we never worry about what the subscripts are. So this would be hydrosulfuric acid. Okay, so again, the hydro, no oxygen. We didn't drop any syllables in here, but if you called it hydrosulfic acid, trust me, I am not going to get upset with you. Sulfur and phosphorus are 2 weirdos that don't really follow these rules, but it's okay. You'll hear it and you'll go, nope, that doesn't sound right. All right, if the anion does contain oxygen, don't write hydro, first and foremost, okay? Don't write hydro. And we'll get to use the ending here of ic or us, and I'll talk about that here in a second, okay? If we have an anion or a polyatomic that ends in ate, like nitrate, sulfate, carbonate, all those that end in ate, you simply drop the ate ending and add ic, okay? Drop the ate ending and add ic. So like sulfate, okay? Sulfate has a -2 charge. So how many hydrogens will sulfate need to have if I wanted to write this as an acid? Because again, as it appears, when we look at this, sulfate ion is not an acid because there's no hydrogen. So we'd have to put a number of hydrogen or hydrogens in front of the sulfate ion to make it an acid. How many would we need? 2. Very good. Since hydrogen has a +1 charge, sulfate's -2. So what we're going to do is we're going to drop the ending on the sulfate and make it sulfic. Now, since there's oxygen, we don't even think about putting hydro anywhere. So we just drop the ate ending and put ic and then the word acid. So sulfuric acid. Okay, now what did I do? I added UR in there. And again, you'll get used to that. But if you called it sulfic acid, you're good. All right, here's some examples. HNO3, is there an oxygen? Yep, so don't even think about writing hydro. Don't write hydro. However, the NO3 is our nitrate, so we're going to get rid of the ATE ending and make it nitric acid. Okay. Try the next one on your own. H3PO4. Pause the video. Try it. Okay. You've had a chance now. Again, the 3 hydrogens here don't change anything about this acid name. However, the phosphate, we're going to drop the 8 and make it ic. Now again, phosphor and sulfur, phosphorus and sulfur are weird. So we're going to call this phosphoric. Phosphoric, even though the phosphate doesn't have the OUR in there. So phosphoric acid, and again, since the hydrogen is present here and we have oxygen, there's no hydro. So phosphoric. So we actually added a few letters there. So sulfur and phosphorus, those are our 2 weirdos, and you'll get used to hearing that. All right. When an anion name ends in ITE, because we've removed some oxygens, either 1 oxygen or 2. Remember, if you remove 1 oxygen, then you change it, say, from sulfate to sulfite. So if it ends in ITE, your polyatomic ends in ITE, drop the ITE and put OUS. So for example, we have sulfite. Okay, so we're going to drop the ITE and put OUS plus a little UR. So this will be sulfurous acid. Okay, sulfurous. The key here is getting rid of the ITE and put OUS. All right, so here's some examples. I want you to try these on your own. Pause the video for just a moment and try to name this. Okay, you've had a chance. We have 1 less oxygen than we started with, so the NO3 is nitrate, so we have nitrite, so the name of this acid is nitrous acid. Okay. The phosphate, PO4, has 1 less oxygen, so it's now phosphite, so this is phosphorus acid. Okay. All right. HNO. Ooh. Well, how many oxygens have we removed from the nitrate? That's right, we've taken 2 away. So what is the name of our polyatomic if we cover up the hydrogen here? Well, we'd have NO with a -1 charge, which has 2 oxygens removed. So we have hyponitrite. So we need to get rid of the ite and make it us, but we're going to keep the hypo. Now, the hypo here is not the same as hydro. Okay, hypo, hydro, 2 different critters here. So the hypo means that we've removed 2 oxygens. It ended in the ITE, so we're going to make it us. So hyponitrous acid. Okay, what is this one? H2SO2. Okay, so we removed 2 oxygens, so we have hyposulfite. So now we're going to have hyposulfurous acid. Okay. All right, and here's a nice little chart to help explain everything. And again, let's see here if I can get some color. Red looks good. So here what I've done is I've made a nice little chart to help summarize all the different things here. And it looks like we're using the chlorate root here. Okay, so notice that we have 3 oxygens here. If I add 1 more oxygen, then I put a per in front of it. So I have my root as chloric. The per goes in front, indicating that I have 1 more oxygen. Notice the charge doesn't change. If I go from 3 oxygens to 2 oxygens, okay, I've removed an oxygen, so that it goes from chlorate to chlorite. And then if I take 2 oxygens away, okay, if I take 2 away, then that means I only have 1 oxygen remaining. So now I have hypoite or hypochlorite. Now if I remove all the oxygens, okay, all the oxygens are now gone, then we no longer have a polyatomic. We simply have just an ionic compound. So it's no longer, there's no oxygen, so we have to use the word hydro here. Okay. Now, this is 2011 that I made this video, and I did not give you guys an example sheet, but I made one up and I'm posting it online. I would like for you to take a look at that example sheet. Go online. Actually, you can print it out. I'm going to make a video going over those examples on that example sheet. If this is beyond 2011, you already have the example sheet in your possession, and go and watch the next video. Hope this video has helped, guys.